Scientists are using the new James Webb Space Telescope, Jwst, to study Neptune's largest moon, Triton, for the first time. Unlike older telescopes, Webb can see infrared light, which is invisible to our eyes. This light can reveal the makeup of Triton's surface, its atmosphere, and even hints of a hidden ocean. Can Webb take pictures of Triton's surface? What is Triton's surface made of? Does it have an atmosphere? Is there a hidden ocean under the ice? Could there even be life on Triton? Webb may help us answer these questions and more. But for knowing this, all you have to do is stay tuned till the end of this video. Triton, Neptune's largest moon, is like a distant enigma in our cosmic backyard, wrapped in a chilly blanket of nitrogen and reflecting back a good chunk of the sunlight that hits it. Triton has always held a certain mystique for astronomers, but now with the arrival of the James Webb Space Telescope, it's like a new dawn in our quest to understand this icy world. Think of Webb as our cosmic detective, but with a twist. It sees things in a different light, quite literally. Instead of just regular visible light, Webb is all about the infrared spectrum, which is like having a superpower to see things in a different way. So, while Webb can't snap Instagram-worthy photos of Triton's surface like a rover would, it's got something even cooler up its sleeve. It can analyze the infrared light bouncing off Triton, giving us a sneak peek into what this moon is made of, how hot or cold it gets in different spots, and what kind of air it's breathing, so to speak. Picture Webb as an artist, but instead of using colors, it's using different shades of infrared to paint a detailed picture of Triton. And trust me, this isn't just any painting. It's like a masterpiece that could reveal hidden secrets lurking beneath the surface. With Webb's infrared gaze, we might finally unravel the mysteries of Triton's terrain, spotting strange formations, understanding its weather patterns, and maybe even catching clues about what's going on underneath all that icy exterior. Who knows? We might stumble upon signs of bubbling activity or hidden oceans, transforming Triton from a distant curiosity to a world full of surprises. Imagine Triton as a colorful map, with each color representing a different frozen ingredient like nitrogen or methane. Webb can read these colors like a book, telling us stories about Triton's past, like if it got smacked by big space rocks or had icy volcanoes erupting. For example, Webb might find spots with lots of methane ice, hinting at old cryovolcanoes spitting out a mix of frozen gases, or it might spot signs of ancient collisions. Triton's chilly air, mostly nitrogen, is also under JWST's watchful eye. It can see where sunlight sneaks through, turning ice into gas. It's like watching steam rise from a cup of hot cocoa on a frosty morning. So, thanks to JWST, Triton isn't just a boring old frozen moon. Gases like methane or carbon monoxide could be clues to some serious underground action, like plumes of warm water sneaking out from beneath the icy surface. But the real jackpot could be below Triton's icy shell. Some scientists think there might be a secret ocean hiding underneath, kept cozy by Neptune's gravitational cuddles. Now, Webb can't peek directly at this ocean, but it's on the lookout for clues. Picture this. Webb spots a hot spot on Triton's surface where there shouldn't be one. It's like finding a warm spot on an icy pond. It could mean there's water bubbling up from below. Webb can't solve this mystery alone. We might need future missions with landers or probes to confirm the ocean's existence and figure out what's in it. But Webb is laying the groundwork by pointing us in the right direction. The observations from Webb are likely to be a game-changer in our understanding of Triton. Let's discuss why. Compositional diversity. Webb's detailed mapping of surface ice could reveal a more complex composition than previously thought. We might discover pockets of exotic ices, hinting at past collisions or interactions with comets. Atmospheric dynamics. Studying the movement of trace gases in Triton's thin atmosphere could provide clues about potential cryovolcanic activity and the influence of Neptune's gravity. Evidence of cryovolcanism. Detecting methane or other gases associated with volcanic activity would be a groundbreaking discovery, suggesting ongoing geological processes on this icy world. Subsurface ocean clues. Identifying regions with anomalous heat signatures or wobbliness in Triton's rotation could be a tantalizing hint of a hidden ocean, paving the way for future missions to confirm its existence. Triton holds the key to unlocking mysteries not just about itself, but about the entire solar system. But how could Webb's observations have broader implications? Well, here's the answer: the origin of Plutoids. Triton's composition and geological activity can shed light on the origins of Pluto and other Kuiper Belt objects, KBOs. Were they formed in the same region as Neptune, or did they migrate from elsewhere in the early solar system? Understanding Triton's history can help us piece together the formation and evolution of these icy worlds. Habitability of icy moons. If Webb provides evidence of a subsurface ocean on Triton, it strengthens the case for the potential habitability of other icy moons in our solar system, like Europa and Enceladus. Studying Triton's potential ocean composition and interaction with its rocky core could inform future missions searching for life in the outer solar system's icy realms. Cryovolcanism and organic molecules. Cryovolcanic activity on Triton could potentially spew out water-ice mixed with organic molecules, the building blocks of life. Studying the composition of these plumes, either directly or through the analysis of atmospheric trace gases, could offer valuable insights into the potential for prebiotic chemistry on icy worlds. Despite the incredible potential of Webb, there are challenges to overcome, like Triton's vast distance from Earth, which limits the resolution of Webb's observations. Additionally, the faintness of its reflected light requires long exposure times, making it difficult to capture rapid changes in its atmosphere. However, Webb is just the first step. Future missions leveraging Webb's findings could revolutionize our understanding of Triton. An orbiter specifically designed for Triton could map its surface in high resolution, study its atmosphere in detail, and potentially directly detect plumes or other signs of geological activity. A lander could provide in-situ measurements of the surface composition, search for signs of past or present water, and potentially sample any plumes that erupt. A combination of an orbiter and a lander would offer the most comprehensive picture of Triton, allowing for simultaneous study of its surface, atmosphere, and potential internal processes. The James Webb Space Telescope boasts a suite of cutting-edge instruments specifically suited for studying distant, faint objects like Triton. Here's a closer look at some key players. Near-infrared camera, NIR-CAM. This powerful camera operates in the near-infrared spectrum, allowing it to pierce through the haze surrounding Triton and capture faint light reflected from its surface. By analyzing the intensity of light at different wavelengths, scientists can identify the specific molecules present on the surface, creating a detailed compositional map. Near-infrared spectrograph, NIR-SPEC. This instrument acts as a light detective, breaking down the infrared light from Triton into its component wavelengths. This spectrum reveals unique fingerprints of different molecules, allowing scientists to not only identify the materials present but also determine their abundance and temperature. By observing variations in the spectrum across Triton's surface, scientists can map out temperature differences and potentially identify regions with anomalous heat signatures. The mid-infrared instrument, MIRI, operating at longer wavelengths, MIRI can peer deeper into Triton's atmosphere and potentially detect trace gases like methane or carbon monoxide. These trace gases might be signatures of ongoing geological activity, offering clues about potential cryovolcanism. Additionally, MIRI can probe the faint thermal radiation emitted by Triton itself, providing insights into its overall temperature and the presence of any internal heat sources. Reaching Neptune and Triton presents a formidable challenge. The vast distance, roughly 2.8 billion miles from Earth, translates to a travel time of over a decade using current propulsion technologies. Additionally, the faint sunlight at Neptune's distance makes it difficult to generate enough power for traditional spacecraft operations. To explore Triton, we have different mission options, using gravity for speed, nuclear power for energy, or smaller probes for specific tasks. But we must be careful not to contaminate Triton with Earth germs and to understand what signs of life there might look like. Balancing exploration with protecting Triton's potential life is crucial.